Welcome everybody to this brand new module looking at motion in 1 and 2 dimensions by SVGS Physics. All rights reserved. I wanted to just put up a quick reminder about what a scalar is and what a vector is. And I looked on images and found this beautiful picture from NASA that honestly explains exactly what I was hoping to get across. A scalar, as a reminder, only has magnitude, so that's just its value. When I say magnitude, I just mean a number. So a scalar will only have some number and its associated units, versus a vector having both magnitude and direction. So some examples. Vectors are displacement. This is how far am I from where I started. Versus a scalar might be the total distance traveled, and that's not listed on this chart here. Other vectors include acceleration, momentum, force, velocity, all that kind of good stuff. Versus scalars being pressure, mass, density, energy, and other things like that. This unit focuses a lot more on a few vectors. So, displacement is how far am I from where I began to where I ended. Velocity is the rate of change of where I am. So, how fast am I moving, essentially, at any given time. That'll be in meters per second. Kind of like your car traveling in miles per hour. But we're all about the metric system here. Also, under acceleration, that's how fast are you speeding up or slowing down. Really, it's just the rate of change of velocity. So we're looking at three different things, each one being the rate of change of the other. So displacement, how much does that displacement change? That's my velocity. At what rate does that displacement change? That's my velocity. At what rate does my velocity change? Well, that's my acceleration. And from talking with Mr. Klein recently, the rate of change of acceleration is actually called a jerk, which a lot of you probably called me upon completing your first lab report. But nevertheless, don't worry about remembering the name jerk. I'm not going to go as far as that. Now, if we're talking about velocity, a lot of people get confused about average velocity versus instantaneous velocity. Average velocity is just your displacement over time. How far away are you, and how long did it take? And that's okay for the big picture. Like I said, driving down 81, how long will it take until I get to Roanoke, Virginia? I can figure out how far I need to go versus the average speed, and I'll be able to calculate how long it'll take. So that's okay for problems like that. But if we're looking at where is something going to be and when is it going to be there, instantaneous velocity is a much better way to go. Now, instantaneous velocity is how fast am I moving at a certain point in time. At this moment, how fast am I moving? You can either observe it directly if you've got photographic evidence or something like that, or you can calculate it given some other variables. And that's what we're going to look at today. How do I calculate where I am at a certain time? How do I calculate how fast I'm going at a certain time based on other parameters of my motion? We're going to start with the position equation. This is good old d equals d naught plus v naught times t plus 1/2 times a times t squared, with only the t being squared there. Where d is your final position, a lot of times it's referred to as final position. I like to refer to it as its position at time t. Because if I'm undergoing some sort of motion, with this equation, you're not only going to be able to tell me where do I end up, you'll be able to tell me where am I at any given point throughout my motion. So in 1 second, 2 seconds, in 3.765 seconds, where am I? And that's what this equation is useful for. What's nice about it as well is that I really only need to know my initial velocity. I don't need to know my velocity at any given time because my acceleration takes care of that. So if I have, by the way, this equation requires a constant acceleration, but if I have a constant acceleration, then I'll be able to tell where I am at any given time just based on my starting velocity and starting position. And t is how much time has elapsed since I started measuring. And that's the position equation. I call it the position equation because the final result gets you your final position. We also have a velocity equation. So to calculate a velocity at any given time, I've got my final velocity, or my velocity at times t, in meters per second, will equal my initial velocity, also in meters per second, plus my acceleration in meters per second squared times time in seconds. So v equals v naught plus acceleration a times t, time. And then we've got this little equation that I like to call the combo equation, and I believe I made that name up. I'm not sure though. But it's basically, if I've got a bunch of parameters but don't necessarily have time, I can still figure something out about it. I may show you this in class, but basically it comes from the first two equations, solving one for time and plugging it into the other. You end up with your final velocity v squared minus your initial velocity v naught squared will equal 2 times my acceleration times my change in position. I write that as a delta d. So again, v squared minus v naught squared equals 2 times a times delta d, where delta d is a change in position. And you'll find this by just taking your final position, or your position at whatever time you're concerned about, minus your initial position. And that's just going to be measured in meters. So it's your total displacement. So let's look at a quick example. We have a fish vendor accidentally leaves a box of fresh fish on the road. A car hits it, causing its contents to disperse. One fish slides with an initial velocity of 6 meters per second, and as it slides, it has an acceleration of 1.5 meters per second squared in the opposite direction because of friction. Right? So friction often slows things down, and we'll look at that once we start talking about forces. But I've got an initial velocity of 6 with an acceleration of 1.5 meters per second squared in the opposite direction. That should immediately yell, acceleration in the opposite direction. That means slowing down. So, how much time will the fish take to slide before coming to rest? And how far will it slide in this amount of time? Okay. Well, let's look at what we got here. I know that it's going to be a motion problem. I'm given a starting velocity. I'm given a final velocity because it comes to rest. So my final velocity must be 0. Anytime something is at rest, it has a velocity of 0. So I can look at the equations that I have to work with to start out. And I got 3 of those equations: the position equation, velocity, and combo. All right. So which one's going to be most useful to find my first problem, which is how long the fish will take before coming to rest? Well, to do that, let's look at a quick list of what we're given versus a list of what we need to know. So I'm given my initial velocity is 6 meters per second, my final velocity is 0, my acceleration is negative 1.5. Now I came up with that by again deciding on which direction is positive and which direction is negative, like I should do at the start of every vector problem. So I'm going to call up positive, down negative, but that doesn't matter because this is all horizontal. I'm going to call to the right positive and to the left negative. And I'm going to pretend that the fish is just sliding to the right as it accelerates to the left. Now what I need is time and my final position. Oh, another thing I can decide on, not only the direction of the vectors, is where is 0. And I'm going to say the fish started sliding at a position of 0 meters. Just to make life a little bit easier on myself. So, now I look at the equations I have a choice between, and what's going to be most useful? Well, my position equation, I don't know my final position, and I don't know time. So I'm not going to hop to that one first, because there are 2 unknowns in it. My velocity equation might be useful, because the only unknown is time, and my combo equation might be useful, because the only unknown is distance. So I can use either one of those. Let's start by finding how much time it will take the fish to come to rest, and then we'll move on to how far it slides. Okay. So how much time it takes? Well, I've decided I'm going to use my velocity equation because that has time in it as its only unknown. So v equals v naught plus at. And I'm going to solve for time. So I'm going to do this before I plug in any numbers, because especially for labs, you're going to have a series of changing numbers sometimes, but you need to plug it all into the same equation. So I find if I can manipulate the equation before I plug any numbers in, A, it gives me more of a clue as to where I went wrong if I have to troubleshoot, and B, it makes it easier if I have to swap a number out for another one in the future, especially if I'm working with an Excel spreadsheet. So, to solve it out for time, I'm just going to do this really quickly, and if you have questions on it, come in class. But I end up with t equals v minus v naught all over a. Now I'll go ahead and plug in my values. So t is going to be, let's see, v is my final velocity, and over here on my givens I have that is 0. 0 minus v naught is my initial velocity, well that's 6.0 meters per second. And my acceleration is negative 1.5 meters per second squared, because it's in the leftward direction, according to how I set the problem up. So I end up with negative 6 over negative 1.5. The negatives cancel out, and I end up with just 4 seconds. And I can double check my units as well. I've got meters per second divided by meters per second squared. Cool. Anytime you divide by a fraction, it's the same as multiplying by its reciprocal. So this is the same as meters per second times second squared over meters. And check it out. My meters cancel. My second squared's up top cancels with seconds below. I'm left with seconds, which is a unit of time. So everybody's happy. I'll put a little green smiley face on here to indicate that. Cool. So 4 seconds is how long the fish takes to slide to rest. Now, how far does it travel in that amount of time? At this point, I have a choice. I can use my position equation, my d equals d naught plus v naught t plus 1/2 at squared. Now that I have t equals 4, I can plug that in and solve for my final position. Or I could hop over to the combo equation, v squared minus v naught squared equals 2ad, solve for d, and either way, it should work perfectly. Just for this example, I'm going to use the position equation just to show you how I can plug in the value of 4. So, my initial position, I already said, was 0. Oh, by the way, I already have it in a form where it's equal to what I'm solving for. So I would like to know d, and I've already got it in that form. It'll equal my initial position. I declared that to be 0, and that's fine. Plus my initial velocity, well, that was 6, times time is 4, plus 1/2 times my acceleration, well, that's negative 1.5 meters per second squared, times time squared. So that's 4 squared, which will end up being 16. Now I just plug this out, and I find that d equals 12. d equals 12 meters. And I can do a unit check as well. I've got 6 meters per second times 4 seconds. Well, that'll get me meters. Good. And I've got, let's see, negative 1.5 meters per second squared times 4 seconds squared. All right, cool. The second squareds cancel. I'm left with meters. So excellent. I've got 0 meters plus 6 times 4 meters plus 1/2 times negative 1.5 times 4 squared meters. And I end up with 12 meters as my final solution. And again, I'd get the same thing if I used the combo equation. V squared minus V naught squared equals 2 times A times my change in distance, which again I said could be d minus d naught. And with a d naught of 0, I'm going to go ahead and just write that as d, the total distance that it slid. So d will equal v squared minus v naught squared all over 2 times a, my acceleration. And now I can just plug that mess in. My final velocity was 0. My starting velocity was 6, so 0 minus 6 squared, all over 2 times negative 1.5. And when I plug that out, well, wouldn't you know it, I still get d equals 12 meters. So, in this class, if you solve it the way I suggest, or if you solve it a different way, I'm perfectly happy. Just show me the work you did on a test, and if it turns out well, then I am pleased. The last little bit I want to talk about in this video is free falling. Now, free fall is essentially when an object has no force acting on it except for gravity. So the moment it loses contact, the instant it loses contact with anything else, and only gravity's pulling on it, doesn't matter if it's moving up, down, left, right, up and to the right, up and to the left, down and to the left, doesn't matter. If only gravity is affecting it, it is considered free falling. So remember that. It is in free fall as soon as let's say I toss this pen that I'm holding straight up. The moment my hand lets go, it is in free fall. It's moving upward, but it's in free fall. Also, it has no acceleration in the x or horizontal direction, and I'll talk about that when we get to 2D motion. But the big point I want to make about free fall is at the top of its trajectory, so when I toss something straight up or when I drop something or anything like that, at its highest height, it always has a vertical velocity of 0. We're going to start with just one-dimensional motion, so we're assuming something moving straight up or straight down. Forget to the side right now. If it's moving straight up or straight down, it has a net total velocity of 0 at the top, always. So I just want to go through one extra example, and we'll reach the end of this here video. JRandomTroll just graduated! Woo! So in celebration, he throws his cap straight up into the air. He tosses it with, oh, goodness. Sorry about that. I just paused recording because I noticed I had a unit, an incorrect unit in here. I had it listed as 7.68 meters per second squared, but velocity is in meters per second. So, he tosses his cap straight up at 7.68 meters per second. And it's asking what is the maximum height above his hand it will reach, and how long will it take to reach this height. So, let's look at a list of givens versus what we need, as well as the equations that we're working with for motion. Okay, so I'm given my initial velocity is 7.68 meters per second, and it's in the upward direction. So right now I'm going to go ahead and say, up is positive, down is negative, done. I'm also given that my final velocity up at the top should be 0 meters per second. I'm not actually given that in the problem. That's just a physical concept that I know and that I need to carry over. Ultimately, I need time and distance. And I can choose between my position, velocity, and combo equations. One other thing that I know, just from being in this class, is that the acceleration downward is 9.81 meters per second squared, due to gravity for any object, including JRandomTroll's hat. So in this case, I'm going to list it as negative 9.81 meters per second squared. Alright. Now, based on these equations, I need to solve for what maximum height will be reached, so what is the new distance. I'm going to start with the combo equation here. Now, the combo equation says v squared minus v naught squared equals 2 times the acceleration times the change in distance. I'm also going to go ahead and say that the place where he releases his hat is defined as 0, because it's asking how the maximum height above his hand, so he leaves his hand where he releases his hat. He does a little freeze frame after throwing his hat straight up. So, I'm going to solve for my change in distance, again, will be v squared minus v squared minus v naught squared all over 2 times the acceleration. And now I'll plug in my values. I've got 0 squared minus 7.68 squared all over 2 times, I already declared it, negative 9.81 meters per second squared. Plugging that out, I end up with almost exactly 3 meters. Right. So he throws the ball, the hat, 3 meters up in the air. Now, how long will it take to reach his height? At this point, I can use either the distance equation or I can use the velocity equation. For me, I'm going to pick velocity because it has fewer terms, therefore is easier, and I'm not dealing with a times squared. So I know that up at the top, the velocity is 0. Well, let me go ahead and solve for time first. So time will be equal to v minus v naught over a. Just some algebra there. All right. Now my final position, my final velocity, I know is 0 up top, minus my initial velocity, 7.68 meters per second, all divided by the acceleration, which is negative 9.81 meters per second squared. So ultimately, it really just boils down to 7.68 meters per second divided by 9.81 meters per second squared, and that comes out to about 0.78 seconds. So the hat makes it about 3 meters high in the air in 0.78 seconds. We'll do a lot more of this in class, give you some practice on a WebAssign, and then we'll start onto two-dimensional motion, which for me is a lot more exciting. If I launch something in some direction, where will it land? When will it land there? It's just ballistics. It's fantastic. Until then, have a good insert time of day you are watching this. Morning, afternoon, evening. Bye.